Manríquez, presidente municipal de Altamira. Muchísimas gracias por estar aquí. Y juntos les hacemos llegar un saludo fraterno al doctor Armando. Quiero agradecer también a los miembros del presidium que nos acompañan el día de hoy. Doctor Jesús Ricardo Ramos Sánchez, rector de la Universidad Politécnica de Altamira. Muchas gracias, rector, por estar aquí. Es un gusto tener que nos acompañes esta mañana. A la contadora pública Cecilia Rocha de Lizardo, directora del Instituto Tecnológico Nacional de México, Campus Altamira. Muchas gracias, contadora. Muy agradecido por su asistencia a este evento. Y al doctor Felipe Caballero Briones, profesor investigador de este centro de investigación y organizador de este evento, EMDA 4. Antes de continuar, quiero agradecer el invaluable apoyo que hemos recibido por parte del doctor Arturo Reyes Sandoval, director del Instituto Politécnico Nacional, para llevar a cabo este evento. Es gracias a las gestiones que ha llevado a cabo la doctora Ana Lidia Coria Páez, secretaria de Investigación y Posgrado, y a su equipo de trabajo, que el día de hoy este evento ve la luz. Mi reconocimiento también para el doctor Felipe Caballero Briones y su equipo de trabajo, que se nota el gran esfuerzo que han realizado para llevar a cabo la organización de este evento y se ve reflejado en el programa de actividades que se realizará en estos 2 días. El día de hoy inician los trabajos de este cuarto encuentro de materiales y dispositivos de Altamira. Serán 2 días de intenso trabajo, sin embargo, prometen ser ricos en experiencias y conocimiento. En esta ocasión, en esta cuarta edición, el EMDA busca reunir especialistas nacionales e internacionales con estudiantes de pregrado y estudiantes de posgrado de la región a fin de establecer lazos y fortalecer los lazos ya existentes en términos científicos y académicos. Es de notar los temas que se abordarán, entre los que tenemos semiconductores cerámicos, polímeros conductores, celdas de combustible, sensores, celdas termoeléctricas, entre otros. Además, se impartirán talleres como análisis de fluorescencia de rayos X, producción de biobaterías de plantas, entre otros temas. Tenemos la participación en esta ocasión de representantes o investigadores de universidades de Malasia, India, Morocco, Iowa, Manchester, Azerbaiyán, Colombia, Honduras, la Universidad Marista de Mérida y Simvestab, entre otros. Estoy seguro que los trabajos de esta semana dejarán mucho conocimiento, experiencias y lazos de amistad de gran valor para todos los participantes. Comunidad, continuemos trabajando para poner la técnica al servicio de la patria. Para dar inicio formal a los trabajos de este cuarto encuentro de materiales y dispositivos de Altamira, les pido por favor me acompañen de pie para proceder a la inauguración del evento. Siendo las 10 horas del día jueves 16 de noviembre de 2023, damos por inaugurado el cuarto encuentro de materiales y dispositivos de Altamira. Muchas felicidades.
Pueden tomar asiento. Todo evento de gran relevancia, al término se procede a dar el tradicional grito de guerra. Invitamos al licenciado Alfonso Lara Rodríguez, maestro decano de este centro de investigación, para que nos concluya con el tradicional vuelo.
Buenos días, comunidad politécnica, honorables autoridades de diferentes instituciones que nos acompañan. Es para mí un honor dirigir la Foro del Politécnico como una entidad que nos ha cabezado siempre y que nos tiene orgullosamente ligados con el Politécnico. Y así les pido que la actividad politécnica, 1, 2, 3.
A todo el personal y autoridades invitadas se les agradece su presencia a este evento y se les invita a asistir a las conferencias y talleres que se llevarán a cabo. Siempre poniendo en alto nuestro lema, la técnica al servicio de la patria. Gracias por su presencia y que tengan un excelente y provechoso día.
Sí.
Ahora sí le tengo que mover hacia acá, ¿verdad?
Déjame listarlo.
Ah, lo vamos a mover para allá todo esto, ¿verdad? Es verdad, no me acordaba. A ver, ¿Tú quieres conectarse con la bocina? No.
Ahorita tenemos efectivamente lo de los dones, tenemos otra varios estudiantes del área de programación que están participando para atender beneficios para la que es bueno, ¿verdad? Con estudiantes que han propuesto que van a de ellos el incremento también de contenido en la cápsula para nosotros es muy importante ya que ha afectado la relación que tenemos nos ha proporcionado la tecnología, nos ha proporcionado que es acceso a información tenemos también la maestría, una maestría y también tenemos para que damos cuidado también de la parte humanista, por ejemplo, para salir para eso. Ahora que está viniendo de Veracruz, ¿verdad? Hasta darle una educación a nivel superior. También tenemos los aprendedores de la compleja todo la parte de los
particularmente para beneficiar
estamos en conflicto con lo que es la Secretaría de Pesca. Entre ellos, hay un trabajando en la área de ecología, están de
nos comentaron que
y está muy bien, ya que esto significa que con esa producción varias familias se van a ver beneficiadas ya que los proyectos de grandes no van a tener un espacio sanitario para el sanitario de campo, que es los alimentos, ¿verdad? Esto les va a ayudar a eso, a que tengan cómo comercializarla, enseñarles el proceso para las familias, para que ellos tengan así un proceso de una manera de cómo ellos tener un ingreso extra y aparte de un hospital de recursos, tener el alimento.
Se convocó por primera vez a todos los que apoyaban a su razón.
Y tenemos ahorita lo que es, pues nuestro presidente es la Cámara de Gonzalo Ventura, Espina Ventura. Entonces, tenemos ahorita, es la primera vez que tenemos a las tres, es Tampico, Madero y Altamira.
¿Cómo beneficias a los jugadores?
Va a beneficiar en el aspecto de que ellos tenemos una vinculación, esa vinculación nos va a ayudar a que tengan ellos acceso a las áreas deportivas, que ellos puedan tener un trabajo.
Maestro, ¿el link quedó el mismo del seminario? No, es otro. El del Zoom.
El de Zoom es el mismo, el de hoy, el de siempre.
El de que me manda a mí, el que me manda a mí. No. Gracias, de verdad.
O sea, se crearon dos nuevos.
Es que no.
El de hoy.
No veo.
Sí, bueno. Sí,
O sea, si le hablamos, ¿por dónde se escucha? ¿Qué escuchan?
También adelante puede quedar lugares.
para aprovechar. Para ver si le escuchamos a ella. Sí, bueno. Bueno. Probarlo. Sí. Bueno. Sí, probarlo. Sí. Bueno, ahí tú lo mueves para presentarles. Queremos escucharle a ver cómo se
Sí, yo creo.
Could you please open your, I don't know.
Sí,
Llámatelo así. Es que no abre su micrófono para ver si lo escucha. Y le hablamos su nombre.
Okay, Fatima, good morning. Could you open your microphone, please? Okay, we can see you. Your mic is closed. Your microphone is closed. We don't hear you. You need to activate your sounds. Yeah, the sounds is not activated. You need to restart your sounds. ¿Dónde se? No, we cannot hear you. ¿Dónde está? ¿Dónde debe de activar el sonido? Ajá. It's, no, not yet. No se lo podemos abrir desde aquí, ¿verdad? No. Es el equipo, ¿no? Ok, se salió. Ahorita a ver si entra. ¿Quieres decir más palabras? Pero, doctora, ahorita empezamos, tenemos un problema técnico con la conferencia. Voy allá para a ver si entra más gente a los talleres.
Sí, ahí vamos a tener que conectarnos.
Sí, que se conecten al Zoom, sí, pero no. Se conectan al teléfono. Yo creo que la vamos a anotar.
Estamos
Bueno. ¿Se escucha, verdad?
Pero tiene que, sí se escucha, pero tiene que ponerse en otra sala. Déjeme ver, espérame.
Ah, ok, por favor, ok. Sí, escucho. Sí, porque también está en línea, hay que conectamos.
Sí, espérame un momento.
Ah, sí, esperando, ellos van a conectar otro.
Doctor Satish,
Sí,
hay que entrar a la sesión de grupos pequeños, donde está su taller.
hay que entrar con un grupo pequeño, la taller. Ahorita voy a dar... hay que entrar con... Hay que entrar con un grupo
¿Van a abrir
pequeño.
la sala?
La taller.
Pasamos a la siguiente.
Doctor Fatima, can you hear me?
Yeah, I can hear you. Can you hear me?
Yes, I can.
Okay.
Question, we have a 30 minutes delay.
Okay.
It could be possible to deliver your talk tomorrow at the same time?
Yeah, possible. Tomorrow is Friday. Yeah.
Exactly at the same time, 10 a.m. at our time.
Yeah, can.
Okay, so please, we will skip this now and we wait you tomorrow same time.
Okay, sure.
Okay, thank
Sure.
you. Sorry
Okay.
for inconveniences.
No worries. It's okay. No worries. Okay. Thank you. See you tomorrow. See you. Bye-bye.
Hay que preguntarle bien.
Sí, si quiere preguntar. Profesor de Barati, are you there?
Yes, sir.
Okay, Professor. We are going to introduce you, so you are to begin now. Yes.
Yeah, sure.
Okay, so our staff is going to introduce you, and then you can begin to share your screen.
Sure, sir.
Okay, muy buenos días a todos, sean bienvenidos al cuarto encuentro de materiales y dispositivos Altamira. El día de hoy daremos inicio al primer ciclo de conferencias y comenzaremos con la conferencia Quantum Molecular Effects in Nanoscale Devices a cargo de la doctora Debarati Roy. La doctora Debarati se licenció en Ingeniería Electrónica y de Comunicaciones en el Instituto Nacional de Tecnología Durgapur en India en 2003. Obtuvo su máster en diseño PLSI en la Universidad de Calcuta. Realizó su doctorado en tecnología en el departamento de ECE de la Universidad Tecnológica de Maulana Abul Kalam Azad en 2021. En la actualidad trabaja como profesor asistente en el Departamento de Ingeniería Electrónica y de Comunicaciones en el Instituto BP Bodar de Gestión y Tecnología en Calcuta, India, desde el 2005. Es miembro IET del DEI y de la Asociación Internacional de Ingenieros de Hong Kong. Sus intereses de investigación actuales giran en torno al estudio de la modelización analítica del diseño de nanodispositivos bioinspirados y también de nanodispositivos inorgánicos, teniendo en cuenta los efectos de la transmisión mecánica cuántica y cuántico-balística. El diseño de nanodispositivos de baja potencia, la modelización ATK-BML de nanodispositivos diversos y nanodispositivos electrónicos, así como también el diseño de puertas lógicas. Damos inicio a la conferencia de la doctora. Puede iniciar. Doctora de Barati, you can start now. Please.
Okay. Thank you so much for your lovely introduction. And a very good morning to all the lovely audience. I think I should share my screen. And oh, okay, so is it visible? My screen?
Yes.
Yeah. Is it visible?
Yes, doctor, it's visible now.
Okay.
Dígale que sí.
Yes, we could see your screen. Yeah.
Yeah, just let me check whether the slides are moving or not. Just, yeah, it's coming. Okay, so let's start. A very good morning to all of you present over here. So, as you know, I am Debaroti from India, and this is my institute. It is in Kolkata. Hopefully, all of you know this Kolkata. This is a city of joy, and it is in India. And now, as you can see, this is the topic of my talk, quantum molecular effects in nanoscale. So, I think all of you little bit know about these effects and these all these features of quantum interference, then quantum ballistic phenomena, what will happen at the position of quantum scale, then quantum molecular effects, what will be the effects. So after a certain range, when we will just to go into the deeper of the nanoscale or molecular scale or the subatomic range, then what will happen? So it is very interesting features. Then I will discuss some of the things, some of the devices. Hopefully it is all the theoretical aspects that we can build up using this quantum molecular effects. So this molecular FET, that is field effect transistor, then diodes, whether it is possible to build up a molecular diodes. So that we will discuss later on. And then molecular switching and its applications. So this is the thing that we will do in case of quantum molecular interference. Interference is a very known to us, this effect. But what will happen if the benchmark is quantum interference? What will happen if we'll go to the subatomic range? Is the same, it will follow the same classical phenomenon, that interference, or it is something like that, but not exactly. So here we will have it is happening that there is quantum interference. Interference means when we are considering, all of us know that whenever we are considering this quantum effects, the particles will move to the wave nature. Now, when these waves are coming together, then what will happen? There is a phenomenon, it's called interference. This quantum interference offers the unique opportunities and which is very much helpful whenever we are doing something related to the quantum devices. So that needs the fine tuning of the charge transport. Charge transport means whenever we are considering the subatomic level, then the charge particles, either the positive ions or the cations or the anions will transfer or move. So there we are considering the wave nature of a particle. And this is the basic molecular building blocks for the constructive or the destructive quantum interference. Here we are considering, in this figure, we can consider that there are two types of interference. One is constructive, another is destructive. So both of these are useful whenever we are considering the transport phenomena of in the quantum mechanics. So constructive quantum interference, you can see in the right hand side, this is the constructive quantum interference where we are considering two particles with their wave nature. We are considering these particles are moving with the same polarity and with the same amplitudes, all these things with same phases. Now, the constructive one increases its magnitude, and the summative or the additive nature will give the constructive quantum interference. Whereas in case of destructive quantum interference, where we are considering the phase should not be equal, and in that case, they will nullify somehow their interference effects. And that's why we are having this type of almost a single line, a straight line of nature that is called the destructive quantum interference, because it will not exaggerate their nature, their wave nature. And this is the somehow the quantum effect in a graphene nanoribbon. So as you can see in the left hand side, this is the plot. So this is the quantum, this is one kind of simulated wave, simulated result that we are getting from the graphene nanoribbon, and we have plotted the phonon band structure. So as it is a subatomic region and we are talking about the nanoscale features or and we are considering the nanoscale engineering, so we consider the band structure for the phonon particles. And here you can see in the left hand side, this is actually the ribbon, that is the graphene ribbon. And in the mid of this, we are having the highest polarity, highest gatherings of the charged particles, and it will decrease into the left and right side. Whereas in the left and right side, we are considering these are the two electrodes, left electrodes and right electrodes. But the main thing that will happen, all the phenomena will happen in the mid of this region, that is called the actually the quantum effect that we'll find from the central molecular region, this way. Okay, and next, this is the band structure. Band structure is a complex band structure. So I am not going into the details of this complex band structure, because these all are related with some very, very complicated Schrodinger equation solving. We need to solve some Schrodinger equation to get this band structure, but this will happen. This is just the output of the band structure that we got for a biomolecular FET. In this case, we are considering, you can see the source is my own paper, and it is atomic scale modeling. of electrically doped pin FET. Now here we are considering one FET, that is the field effect transistor, and we have given the polarity into the or bias in the two end of the electrodes, and we are getting this type of band structure. Now you can see the bands are not exactly the same in this case, and some dotted lines are also there. That means it is distracted. So what will happen, as I told just before, that the interference is highly affected due to whenever the charge transport from one part of this FET to another part, then it will not remain like a straight line or a smooth line, or it is a distracted one because of this the interference, because we do not know exactly what will happen at the subatomic range, whether the wave particles are in the same phase or not, that we can't imagine, because after this when they will coming to the subatomic range, the phenomena may happen, either it is a destructive one or the constructive interference will happen. When we are getting the constructive one, then the smooth line is appearing. But when it is a destructive one, then small this type of dots are coming. And this is the device that we have used one simulator to design this type of molecular devices. In the right hand side, this is the actual theoretical model of this device. This is actually a nanotube like structure. All of us know about this CNT. This is very upcoming and very popular device nowadays. This carbon nanotube, this structure is very well known to all of us, and we have studied the same thing. We are trying to build the same type of theoretical model using the thiamine. Thiamine is one of the you can say the part of DNA. Okay, so just by using this DNA, it is like structure, not exactly, and we put a metallic gate in the top of this structure, and then if we give the as you can say bias we have put in the left and right electrode, that we will have this type of this is the actually the electron concentration in this side. And we can see again the transport phenomena is mainly focused out in this region, the central molecular region, this region. Okay, whether the left electrode and right electrode are just completely alone without this effect. Okay, and if we get this, and if we also change the doping concentration, then we this is the electrical doping concentration, and if we change these values, we can say this is the current. With the change of voltage, we are getting this type of current, and you can say that this type of things are almost similar with our conventional semiconductor devices. And this is the quantum ballistic transmission effect, where we can see this is the transmission spectra for another structure, the same thiamine we have used, and we are getting this HOMO and LUMO plot. And HOMO and LUMO is very basic things from where we can justify the structure thermodynamics. That means HOMO is the highest occupied molecular orbital, and LUMO is the lowest unoccupied molecular orbital. And when the gap between these two are very close, then what will happen? The barrier between the one terminal to the another terminal of the molecular device is lesser, and that means the charge will transport much more faster, and the device may be much more getting faster. But when it is much more, then though the thermodynamic stability is higher, but the charge transport is lesser. So we are considering that for the Jahn-Teller effect, we are considering that the moderate one, That means not much high, not much less. That gap should be ideal for this getting good quantum ballistic transmission effects, and which is the fundamental thing or fundamental phenomena for any molecular transmission. And these all are the results that we have obtained from our modeling, from our device. And you can see the right hand side, we are considering the multi-sim. We have used multi-sim simulator. These all are the logic gates, and all of us know the functionality of logic gates, and we are considering only OR and NOR gate. And here the left hand side, we are getting the output from our molecular device, theoretical device, and in the right hand side we are getting the multi-sim simulator result, and you can see these are almost similar. So here it is proved that the conventional one, this molecular effect is just almost nearly equal to the conventional one. This is some of my paper, and from where we are getting this type of devices. So these all are the quantum molecular switch. Here we just tried to implement one quantum molecular switch. Here we are considering one cytosine. Again, this is cytosine is another protein part of this DNA, and you can see for on and off condition, we are having the two their features will not features their appearance will be changed. It is rotated. It is rotated just 90 degree twisted form. So it is rotated at 90 degree, and it is two condition. Another is one on condition, another is off condition. And then this is another one from my publication, and here we are having this transistor. This is again ANT, that is called ANT, that is the adenine nanotube like structure. This is and this is providing this type of results. Okay, this is almost similar with the conventional one, and these all are my papers, and these all are the publications. Okay, so I think that's all from my talk. And if you have any question, please ask.
Okay, ¿alguien tiene alguna pregunta? ¿O algún comentario que quieran hacerle a la doctora? Sí.
You hear me? Hello?
Hello.
Yeah.
Yes, sir.
Maybe I have two questions. The first one, which code are you using? Because I saw that you're using like first principle approach. To
Yeah.
one. So which code are you using?
Yes, sir. Actually, we are considering this density functional theory to simulate all these results to make the theoretical devices, and these all the results are DFT based.
Yeah, but which code are you using? I know that it's different.
Which simulator you are asking?
Oh, so the DFT is the theory, but which code are you using to develop this theory?
Yeah, it's a quantum wise, that is the simulator that we have used. It will give both the DFT and as well as the NEGF, that is non-equilibrium gain function based results.
Okay, when you present the phonon spectra, yeah, I saw that you have the imaginary part. So this imaginary part help you to interpret some kind of, or yeah, it's help you to have a good like interpretation in your application, or yeah, if you
Yeah. Sir, this one, I think, yeah. This phonon band structure, this is not from my publication. Actually, that I have captured this from the source that I have mentioned. This is from the quantum etiquette. This is the simulator that site they have given. And this is the band structure for the graphene nanoribbon. They are using the same simulator, and I have taken this from this source only.
So no, but I just want to understand. For example, in this case, when they talk about the quantum effect, you should like to have an imaginary part in your phonon, or not. If you have an imaginary part, what can help you? If not, what?
Yeah. Yes, but in this case, we are considering only the charge transport phenomena, and here we are considering as because of the we are giving the two opposite sides of doping in the electrodes, and we are having this band structure for the complex band structure, and almost it is nullify the real bands. You can see it is a red dotted one, and it is almost zero. Means almost we are not considering the particle effect our for our device. Whereas whenever we are going for the complex band structure and we are getting the wave nature, then we are getting a good complex band structure compared to the others. So here we are considering we are generating, we are provoked with some charge particles from the two ends by you can say by the injecting the charge particles from the two ends of the money source, and one is drain, and we have given this by applying bias.
Good morning, Dr. Barati. Thank you for the talk. I would like to do a short comment in Spanish in benefit of our students that are from BAC, if you don't mind.
Yes, sir.
And then I will ask a question later. Let me comment something to the students in Spanish. Bueno, como vieron, el trabajo de la doctora se trata sobre electrónica molecular. No estamos hablando de hacer electrónica con moléculas pequeñas, por ejemplo, con adenina, con citosina, con grafeno, ¿no? Que es otro nivel de la electrónica que conocemos usualmente, que está basada en silicio, ¿no? Entonces, esto es es un avance, digamos, es lo que sigue la parte de electrónica, ¿no? De electrónica molecular. Entonces, le quiero preguntar a la doctora qué tan cerca está lo que ella hace, o lo que se hace en general en electrónica molecular, en dispositivos ya reales, en dispositivos que ya podamos, con los que ya podamos trabajar. Eso es lo que le quiero preguntar. A ver si quieren ustedes preguntar algo, si lo puedo traducir, para preguntarle en inglés. Si alguien tiene alguna pregunta, antes de que yo le diga. En inglés y en español, y se la traducimos. Doctor, I was telling them about the molecular electronics, that is a very new subject in research. And the question is, how close is now the studies to arrive to real life applications?
Yes, it's very important for the real life application. Though it is a theoretical things that we have applied, we are applying this the DFT, NEGF, all this first principle formalisms. But the thing is that as it is very effective for the quantum ballistic transmission effects, and nowadays it is the era of quantum computing. So until and unless we are knowing the what will happen below the sub or in the subatomic range, until and unless we know what will happen exactly, what is the interference effect, we do not know what is Cupid, how they will work, and until and unless we do not know this wave nature of the particle, we do not know even the 3 stages for the quantum computing for the qubits. So I think this is one step ahead for the quantum era. So and also this is how we should know the quantum superposition. So because it all are related. Though it is theoretical, but in near future, I think it's very much effective whenever we are talking about the qubit and the nature of the qubit, how they will interfering, and how we will build a supercomputer or this quantum computer.
Okay, thank you. I will translate a bit for the students. Okay, efectivamente, esta electrónica molecular está pensada sobre todo para computación cuántica, como probablemente han escuchado, es lo que sigue en términos de computación. Hay prototipos ya de computadoras cuánticas, y el trabajo que la doctora hace es principalmente para entender a nivel teórico cómo deberían de funcionar estos dispositivos, cuáles son los factores que los afectan, etc. Entonces, es fundamentalmente lo que hace la doctora. No sé si tienen algún comentario, algo que quieran preguntar aparte. Pero sí, por favor. Okay. Doctor, thank you very much.
Thank you, sir. So, shall I stop sharing?
Yes, doctor, please. And thank you.
Thank you, organizer, for this lovely conference. Thank you so much.
Thank you. We thank you very much for the conference, and we expect you for the next edition of this conference. And if you want to stay with us, you are welcome. Yes.
Thank you, lovely audience. Thank you.
Ya está conectado el otro momento.
Es la doctora Jaime. Vamos a continuar con la siguiente conferencia, y está a cargo de la doctora Halima Sabi, que está aquí con nosotros.
Yeah, hello. Excuse me, dear organizer. Yeah, actually, yeah, Professor Philip. Actually,
Yes.
it is already, yeah, it is already 10:30 p.m. at India. So,
Yes, doctor, please. You
yeah,
can
so
disconnect. No problem.
yeah, so I'm leaving now, and hope this will be a wonderful session, and I wish this conference will be successful in all regard.
Thank you, doctor, and we're
Debarati, yeah.
nice to hear you. Thank you very much.
Yeah. Thank you so much.
Namaste.
Buenos días, vamos a comenzar. Gracias. La siguiente ponencia lleva por nombre Electronic Properties of 2D Systems as Initial Study, impartida por la doctora Halima Sari. La doctora Halima Sari es una destacada física especializada en materia condensada. Es doctora en física por la Universidad Mohamed V de Rabat, en Marruecos. A lo largo de su carrera ha realizado importantes contribuciones en diversas áreas de investigación, especialmente en el campo de materiales de conversión de energía, materiales termoeléctricos, materiales magnetocalóricos y materiales semiconductores. Su experiencia ha sido muy solicitada, lo que ha llevado a participar en numerosas escuelas internacionales de prestigio centradas en el cálculo de estructuras electrónicas. Les doy la palabra a la doctora.
Firstly, I want to thank Dr. Philip to invite me in this meeting. And my name is Halima Sari. I'm professor in physics in the Constantine Laboratory in Faculty of Science of the as I said, we work in a Faculty of Science. Our team under supervision of our leader, Professor Yusuf, and my professors and PhD students. We work in different thematics like solar energy, study of magnetic properties of materials, using simulation and numerical application. That's why my talk is about theoretical study of the can you just next slide. It's fine, it's fine. Next one. That's why my talk is about application of 2D materials using theoretical approach, and I will give simple illustration how to use DFT for photocatalysis application. So, 2D materials, as you know, the most famous example is graphene, as it's known that having interesting properties like mobility and solubility behavior. Then we have many other examples like carbon graphite, black phosphorus, and so on. And these materials can be used in different applications, like solar cell, photoresistor, and different applications. As you can see here, we have solar energy, photocatalysis, and gas sensor. These the most application, important application that can be used or that can be applied for 2D materials. So the question is how we can adapt any material, or how we can decide if any material can be used in such application using experimental or theoretical study, and how we can do this. So we find the most application as now, like photocatalysis, electronic magnetocaloric effects, and energy storage. The first example for photovoltaic application, we need semiconductor material having bias band gap, and this value of band gap must be close to 1.5 to 2.5 or 3 electron volts for the visible parameter. And in this, for this semiconductor, an electron existing in valence band can absorb the visible light to be excited to conduction. And so we have photocurrents created. The first example for solar energy, as you know, that's silicium, and then we have different components like perovskites, known as they have interesting stability, good absorption, and good efficiency. But the problem with this material, some perovskites are not stable, and they have atomic toxic atom. So the next example is the spin. For this application, we exploit the spin and charge of electrons to get more storage of information, as we can use this material for the magnetic memory, or magnetic memory, or dynamic magnetic memory. We are looking for magnetic material or semiconductor. When, as you can see here, this is zinc oxide with the rare earth material, and we found that in this case we have had metallic behavior. Also, this material must have ferromagnetic phase. For magnetocaloric effects, we're looking for magnetic material having interaction with magnetic field, and when we apply magnetic field, the spin of atoms are unique in the same direction. This is the order of the system. And when we remove the magnetic field, we have disorder of the system. And this phenomenon can be created
the cooling or the heating of the system. So we're looking for magnetic having large magnetic moments, large entropy change, and reduced change in adiabatic population. So using this equation, we can compute these parameters, and we can decide if our magnetic or our components are that can be used in this effect. The last example is battery. In this application, we must specify if we are looking for anode or cathode battery. And because the difference in voltage between two electrodes can increase the diffusion energy and the mobility of ions with an interaction of two materials. So the most important parameter is voltage and diffusion energy and the capacity. And this parameter can be calculated using this formula. As we know, based on this application, we can take any components. We can test by experimental tests. Like we can search experimental conditions like temperature, pressure, or elaboration method to make scientific of this material. But the question, this technique requires more time and cost. So if we have choose the good theoretical model to model this in order to describe the physical properties and solve this problem of time and cost for experimental tests. So the model must define or describe the good phenomena for any components. And this model must be based on some information of crystal structure components and numerical simulation. And this requires more knowledge about informatics and about polygon and background in physics, like how to resolve Schrödinger equation, quantum mechanics, and solid state. So this model can be described the physical properties like optical transfer and magnetic properties. Our model is DFT, density functional theory, which is based on Schrödinger equation or the resolution of Schrödinger equation. As we can see here, the Hamiltonian of the system, it seems to be complicated because we have much more parameters like kinetic energy of the nucleus and the kinetic energy of electron and the interaction of electron nucleus and electron nucleus. So we have more interaction in this system. So to resolve this equation, we must start by simple consideration, like this approximation. We will consider, for example, when we neglect the kinetic energy of nucleus, and we start by the simple atom, is hydrogen, having electron or charge positive and negative. So this is called single particle approximation. And the first approximation was Born-Oppenheim approximation. So when we have many particle systems, like much more electrons, we have much more correlation between these particles. And this problem is called like term of exchange correlation. And this term is resolved by Kohn-Sham equation. As you can see here, we have much more interaction between particles, and we can consider these particles under the effective potential, like manifold theory. So based on this equation, we can have this equation where we have kinetic energy of electron, potential of Kohn-Sham, like potential of exchange correlation, and the basis of function and the eigenstate of energy. So the potential of the exchange correlation potential is treated by different approximations. The first one, local density approximation,
In this approach, we consider electron as homogeneous gas electrons with constant density. As we can see here, the density for in this case is have this formula. And this approach is specified for specific for the atom having S and O and P orbital, because we know that these orbitals has the spherical form. So for the d orbitals or f orbitals, we have the density is not, or the orbital is not spherical. So we can include the density and the second, the first derivative of the density. So this is called GGA approximation. And the third approximation, we add, it is based on GGA approximation, but we consider the second derivative of kinetic energy. And so the last approximation is hybrid action, when we have the relation between DFT and the Hartree-Fock equation. And for this parameter, like relation, we must be discussed as a function of the material and the height of matter. So applying this approach using DFT, we get in this picture many different examples of material, and we have here problem of underestimation of band. We are looking for the points band compared to experimental one, but we have here the most cases we have the calculated band is much more underestimated, but compared to experimental. And this problem is resolved by applying coexist approach. So we have many examples of this approach, but I can present here just one example of GW approximation. It is an approximation made in order to calculate the set energy of main backup system. And this approximation is expressed as a term of expansion, like developments in mathematics. And we have different orders of GW. So we're looking for the first order, like this term. And in GW, we have two terms, G, which means Green function, and W is the string. So GW, or Green function, have two parts. The first part is the scalar product of two wave functions, when we add an electron to the system. And the second part, when we remove an electron from the system. It seems like we can measure the propagation of the particle between two positions. So for green function, we're looking for the pole of solution of this equation, and we can calculate the excitation energy like experimental, as we can do in experiment like photon emission spectroscopy for two cases, inverse and reverse photon emission spectroscopy. And the second term is W, which means gradient, and all correlation or electronic potential for between two electrons. As we can see here, this potential is different as function of the medium. The vacuum is different and compared to other mediums. So this parameter or this idea must be included, must be introduced in this equation, like the electric function of this medium. So we take into consideration the electric function of the medium and the charge of the two particles and the distance, of course. To sum up this part, we have, yes. To sum up this part, we have different approach of theoretical method. The first one was DFT, based on constant equation. The problem of this equation can be, or the good point can be reached, we can reach the good behavior of the system. But the value of the band gap is underestimated, because, as I said before, we have the term of exchange correlation term is unknown. And this problem is solved in GW equation, when we have, we take into consideration the quasi-particle energy and excitation of particles between valence band and convection. So, using GW approach, we have no more problem in that gap. As you can see here, we have the computed band gap are much below or equal to that experimental band. And in this figure, we have different coexist approach. The first one, based on DFT, we can use this approach for hybrid function or GW. But it seems in the most results that GW can give us the good behavior properties. So as I said before, now I will present some just an example for this application. The first step is to define application and to search which condition must be verified by material. So in photocatalysis application, we are looking for the semiconductor having their standard, and the valence band and conduction band H must be localized between the redox potential of these and the band gap must be greater than this value. So an electron in the valence band can absorb the visible light to move to electron to convection band. And this electron, excited electron, is reduced in this reaction to produce the hydrogen, and this rule or this place is replaced by electron released from oxidation. So the first step for applying DFT, we need some parameter like lattice parameter, crystal character, and atomic position for system. So we can choose the good choice for exchange correlation like this approach, which one we can use for any calculation, and the basis for wave function. It's like Gaussian or plane wave expression, and the formalism for this approach. I don't know if some person here use DFT, because we have many codes apply DFT, but the most code, as we can see here, was quantum espresso and image. So the formalism of the pseudo potential is implemented in the two code, quantum and VASP, and the full potential is implemented in bridge. So the step 3 is to apply this parameter to compute the density of state and to search the energy level of this system. And we get the band structure of this system, and we can describe much more properties of a system. So for photocatalysis application, we are looking for also the band gap and the band edge, like the valence and connection band. They are computed using this formula. And when we apply this DFT to our components, like perovskite, for example, we have here a problem for this material, like titanium oxide. We have band gap except the band edge and except the good value for photocatalysis. Or the band edge are much more, they are not localized between these potentials. So how we can adapt any material to be applied for photocatalysis application? So we can think as the first idea is doping this material by some elements, and we can control the band gap with these elements. As an example here, I present titanium oxide having band gap except 3 electron volt. And when we dope it with selenium, we get the band gap close to 1.7. That's good. And the absorption is shifted to visible edge. That's good also. Other example here, we have perovskite material. When we dope it with different material or co-dope it with different material in different sites, we are looking for the stability. As we can see, the formation energy is negative. the band gap is reduced, and the quantum efficiency is enhanced in the visible range. So we can see that doping is the characteristic of this application. The second solution is the heterostructure. There are many papers treat this case. So we are looking for two materials having almost the same symmetry, same lattice parameter, and we can compute also the work function to know in which direction the electron can be moved, from which semiconductor to another. Also, we can compute the density, the charge density at the surface of this material, and we can see the electronic or electrostatic potential in this state. So for Z-scale, for this application is applied. It is applied for different applications like the quarter splitting and degradation of pollutants. So to sum up this talk, we have many examples of 2D system or 3 or bulk system. So how we can define an application for this system? We are looking for using theoretical approach. We start by lattice parameter, distance factor, and then the good choice of formalism and the good choice of approximation can give us the characteristic risk. And we can decide if this result is experimental results, or we can have deep analysis of real phenomena in this system. So, yes, I can start.
Si alguien tiene alguna pregunta, algún comentario, también lo podemos traducir. Bueno, doctor. ¿Alguien? Sí.
Which programs or softwares did you use for the simulation?
For this example, I did.
Yes.
And quantum is. So in this, for this example, this is done for this paper. This is done by Windsor Clayford. And for this example, it's done by quantum inspection.
So did you guys base your research to do the simulation first before the experimental part?
We don't say that in the series, but we just looking for about status information, and then we can use them for simulation. So the other experimental, we can compare like this surface state of charge density or the band experimental band compared to theoretical band.
For me, it was interesting before about spintronics. I have never heard.
Can you move to yes, slide? What? Wait, number. Next to the first.
This is for electronics, materials for electronics.
Oh, nothing.
Matrix?
Magnesium.
Okay. So do you need to change the speed to obtain your or not?
You're looking for magnesium. So to found hard by this rule. Now this is done as I said. But the sample is not manual. But we don't with magnesium material to get this behavior. So the contour of the magnesium behavior doesn't have it in total.
And several materials can be transformed or acquire this property, or just some materials.
We can remove the number and this by magnesium material to get this.
Okay, thank you.
¿Alguien más tiene alguna pregunta? Bueno, también.
So this is the theoretical part, but in the experiment part, in what kind of moment or experiments you can use it?
You can use it.
In what moment?
Just experimentally, but you can use it for comparing our intelligence, just for comparison. Okay, to compare both sides. So we can predict similarity, we can predict the end of the system, but we can improve these results compared to experiment.
Thanks.
Does this count as some sort of electromagnetic induction?
I ask if this counts as some sort of electromagnetic induction. Electromagnetic.
No.
No. What would it be exactly?
I don't understand.
How exactly do you do it? Because I did not understand.
How can I say to you?
The process.
Yeah.
Process.
Yeah, as I said, we're looking for practice, experimental practice, and then we can use them to test using the air. And for example, like this, we obtain, so this is the density of state. As you can see there, for example, state, which presented by Valérie, it's semiconductor having the band. And this element is opposite here, is the state of this element is placed in direct in black. So we can see here that this is the half. So this format or this form is called the half.
It's just to apply certain characteristics to the material. Okay.
¿Alguien más tiene alguna pregunta?
Solo para explicarles, el DFT es una herramienta para reducir o también para confirmar los resultados experimentales. En dado caso, cuando no hay una explicación bien profunda de algún experimental, de algún análisis que hizo un grupo experimental, siempre pide la ayuda a personas teóricas, como el caso del DFT, para poder confirmar, pues, no sé, algún tipo que salió ahí o alguna fase o porque el DFT es un trabajo muy profundo que haces varios ejemplos, varias pruebas para poder tener como la explicación. No sé, por ejemplo, hablo del Spintronic. El Spintronic es una aplicación, por ejemplo, en el EMRAM o también en las lecturas del disco duro. Ahí porque saben que es un binario 0-1. Entonces, para comunicar la cabeza, puede ser, la cabeza del lector con la información que está en el disco o en el CD del disco, pues empiezan como a descifrar 0 con 0, 0 con 1. Entonces hay que tener un elemento magnético que tenga esa variación de 0 a 1 para poder como comunicar el lector con el disco, con la información que está en el. Y pues por eso necesita un elemento magnético que tiene un pico en la energía de Fermi, porque ahí es la energía de Fermi donde está el pico verde con el pico rojo, y ahí debe tener solo una dirección, si es un spin up o spin down. Y desde ahí empieza a leer o descifrar la información que está contra el lector y pues la información que está en el disco. Pues esa es la ventaja de.
Ok, vamos a darle otra vez un aplauso a la doctora.
Hagamos una pausa. Sí, ya